to go push from the scene from Cloud 9 and said you need to do a pull request first or make it.
Okay, fair enough.
So I think the problem still exists, but you're right, probably more.
Okay, so let's go here. Oh, that's my fork test.
It doesn't necessarily override that part. You don't have that file on your system unless something else.
Yeah. Okay, so the quiz talks about some of the limitations we talked about last time, and that every one of you should have experienced in working on the homework assignment that was due on Friday, right? So creating a child process is simple. You get all the copy. You get a copy of all the memory, everything you have, but it's a copy of it. Life would have been so much easier if you had that array was a shared array among all of your copies, correct? Unfortunately, that wasn't the case. Why do you think that's not the case, first of all? How come the Unix people who wrote the fork system call didn't just decide, you know what, if they're creating a second process, why shouldn't we just give them memory access between these? What's the limitation of that? Go ahead.
Well, your two child processes could end up blocking each other or overriding the code that one just wrote. So if one child is trying to alter that array, like move something around with it, the other child could be trying to do it at the same time, or it could overwrite the other.
So you're talking about file locking?
Yeah.
Yeah, I'm talking about, forget about I/O. I'm talking about if I have an array in the original parent, and I call a fork, and I create one child, two children, it doesn't matter. It would have been nice for us in that merge sort situation to be able to have the actual shared array. One array, one memory address, it doesn't matter which child or parent or whatever makes a change to it, you're changing to one place. That would have been nice for us. And then we could have, played the lock game, if you will, with a couple of variables inside of our code that were also shared. Why do you think that's not the way it by default works? Go ahead. Well, that is the case. That what you just explained to me is what it actually does. So fine, I'll ask the question again in terms of your answer. Why does it work that way? As opposed to why doesn't it work the way we wanted it to work?
Because it's not giving you a reference to the memory address.
He's just flipping back and forth. Look, it gives you a copy complete thing. So okay, fine. Why does it work that way? Because it doesn't give you a reference. It's like, okay, well, why doesn't it give you a reference? What it does is it makes a copy.
I'd be a great politician.
I don't think you're hearing me. This is the greatest non-answer in the world. So what we're trying to do, we're trying to understand the underlying rationale here. When they wrote the fork system call, and what we're going to see is this is true across many system calls, why did they specifically make the decision that when we create a child process, that child process gets a copy of everything, so you kind of have a nice, comfortable starting point, but we're not going to duplicate, we're not going to, Ghostbusters terms, cross the streams by giving you access to the parent's specific memory. Why do you think it, was that phrasing?
Yes.
Was it?
No, that's like an actual movie.
Yeah, when I start by saying Ghostbusters, I think I'm okay.
If you just said crossing streams,
Then it gets weird. Yeah, I get it.
Then who knows who the children are?
Right. Man, that just brought up such a funny memory. All right, so I'm not going to be able to get it out of my head now. So some of you have probably heard this before. It was must have been about 5 or 6 years ago. I was at a gym, if you can imagine. And I was in the locker room, and there was a special needs guy that his mom would come in to work out, so he would sit there and around. Seemed like a nice guy, but so probably in his 30s, but probably mental age of 4 or something like that. Not certainly special needs. So I guess he must have had to really go to the bathroom, and I'm in the bathroom getting ready to go to the hot tub, and he comes around the corner and he's ready to go. Okay, everything, the equipment's out, and I must have been in his spot. So, speaking of crossing the street, just pees all over me. And I'm thinking, okay, we had a misfire. We're gonna get things. No, yeah. No, there was two urinals there, and the one one of them was open. No, you wouldn't have it. So.
Oh my god, I don't even know what I would do in that situation. You just gotta keep going. You can't pitch it off midstream.
So, now what's funny? So I have a pretty decent personality, I suppose, when it comes to that stuff. And without going into tons of detail, he wasn't getting my clothes wet. So I was getting ready to go into the showers. So in any case, I'm thinking, okay, he's gonna fix his positioning and all this. It doesn't. He starts. It felt to me like drawing. I don't know if he was like writing his name up.
I was here. He was writing LOL.
So, but I thought after the fact that there was a couple other guys. They were kind of real jerks, and if it had happened to them, I mean, the kid might have gotten hit. So, I mean, couldn't have happened to a better person, because I got a good story out of it. And just like, I don't know. I was really actually standing there trying not to bust up laughing.
It's like one of those detectives.
And you could tell he really had to go, because you could just feel the pressure. I'm like, I've been there. All right. So now we got the crossing the streams out of our system.
Been there. In a restaurant.
All right. So what were we even talking about?
Ghostbusters crossing.
Oh, yeah. So why is it the fork system call makes that decision to not give a copy of the memory? Well, not give a pointer. So not give a pointer to the same memory to its children. Why do you think that is? What's the negative side effects of that?
They would be overriding each other.
Okay. In this particular case, because of what we were trying to accomplish, it would have been nice. Kind of what we wanted, right? We needed to have some sort of access. But as a general rule, that creates a dangerous precedent, right? Okay, go ahead.
Like, say the parent had something in it, or had a list of array or whatever, and then it spawned a child, and that child spawned another one, but changed something in the array when the parent wanted that to be exactly what they got.
Mm-hmm. Yeah, so on one hand, we have a situation where it's always locked down. That's effectively how it does exist, right? And we can use that as maybe as a starting point to make a good guess at how different system calls might work. It seems like the mentality is we're not going to make any decisions for you. Instead, what we're going to do is we're going to give you an initial starting point so that the program can keep running, especially because the way the fork system call works is that effectively it just says, create a child, keep going from here. Well, that means if you're going to keep going from here, you have to be able to rely on things that were local variables 2 lines ago, right? So that's a requirement. They had to give... You shaved.
What?
I mean, you've been scaring the crap out of people, and this is... I mean, it's not good, but it's better.
What made you think of that?
I run an octa-core here. So, all right. So in any case, they don't make any assumptions about how you might use the child processes. The only thing they can do is make sure they preserve variable scope. So from that point forward, after we do the, did we do a fork command here? Well, we commented out. Right after this line of code right here, from that point forward, any variables that we defined up here have to be available to both the parent and the child. From a scoping perspective, otherwise you start having errors in your program. And that's an impossible workaround, right? If the very next line of code, before you even ask, am I the parent or am I the child, if you use one of those variables and it happens to be that the parent has access to it, the child doesn't, then the children just immediately die. You have a segmentation fault because they didn't have access to some variable that they should have. So when you look at it from a system call perspective, it was the only possible choice to make sure you can preserve scope. But now they have to ask, is it the same scope or is it a copy of the scope? Okay, and as Tim pointed out in detail, it in fact is a copy of the scope. And the reason they've done this is so they don't make any assumptions about what you might do with the child processes. They also had full knowledge that it would be handy for us to have access to shared memory between two processes. And they have a whole suite of inter-process communication stuff that we're going to start learning about that will provide those mechanisms when they are needed, rather than provided as a default behavior. That make sense? Now, having said that, before inter-process communication existed, and we just had file I/O, what we saw last class is we could have accomplished, let's call it, ghetto inter-process communication. We could have pulled it off. It wasn't going to be fun. It wasn't going to be easy, but it would have been doable. And that's pretty true of technology in general. Before we had multitasking, at some point in time, somebody said, well, I kind of want these two things to happen at the same time. How can I fake it? And then it became a new standard. All right, so that assignment, the purpose of the assignment was to stumble you into that wall, put yourself in the shoes of somebody who's having to write code before inter-process communication is a thing. And it wasn't a comfortable place, was it? Did you even try to do the homework? There's a whole bunch of these people didn't. Did you get a good grade?
Yeah.
So I gave good grades to a lot of people if they put in a good effort. And I gave just zeros and nasty remarks to a bunch of people.
Fair.
Fortunately, I didn't have anything to grade for that. nothing to reply with an ad. How are the eyes, by the way? You're seeing 50.
Up there when you were talking.
You're seeing 10-10?
Oh, yeah, it's the same thing.
Huh? I don't think it's the same thing, is it?
No, well, 10, well, not that.
10-10 is better than perfect.
I mean, I think pilots.
10-10 is the same because it's saying that you see 10 feet in front of you as it's 10 feet in front of you, which is the same thing as 20 feet, 20-20.
If you want to impress someone, you do like a million.
No, but I thought like if somebody has 20/15 vision.
It's saying you see it at 20 feet, but it's actually at 15 feet. It's 15.
Oh, your 20/15 is sharper.
Okay.
15.
Okay, so 20/10 would be awesome.
There's
Yeah.
25. They told me that you could.
Actually, I think it's 15-20, saying
No,
that you
it's
see it at 15.
2015.
Is
It's yeah.
20.
2016. I don't know what you guys are talking about.
Yeah.
So
yeah.
I have 21-inch vision. My eyeballs are telescopes. All right. So shut up.
Yes, Dan.
Okay, so let's introduce, some of you have already looked at this, let's look at how the wait system call works. Okay, so we're going to introduce a couple of more tools to our toolbox. Now everybody for today should have written a plain Jane merge sort, right? So now we have access to a solution for merge sort with all of the beginning and end, all those numbers all work now. So we have a confidence level for merge sort. All right, so now let's throw a couple tools in that will help us write this multi-process merge sort. So let's start off by doing this. Maximize that. We're going to do man wait so you can see the system call for this. Huh?
It's a little small.
Should I make it?
She said.
All right, so I need to do this. I make this one like that, and then this.
That worked so well.
Do I need to quit out of this first?
You need to make
Is it close that first and then open the?
I think it's under.
Or didn't you have to make?
I don't think it's zooming in of the.
Oh.
There it is.
Browser.
Full screen first.
Okay, well, whatever. All right, is this better?
Yep.
All right, so first of all, this guy lives inside of syswait.h, and we also need types.h to deal with some of these PID types, and a lot of these things are just integer wrappers, but in order to actually call it a PID type, we'll need the types.h. All right, so what does wait take? Well, wait takes an integer pointer as a parameter. All right, so that is, we are passing a memory address into the wait system call. The purpose of this is to allow the child, the recipient of the wait, to communicate back to the person who's waiting their exit code. This goes back to what we talked about. I'll just mention it. In Unix, the typical C programs have a return type of int for the main method, because Unix applications typically return a number in terms of their exit code, what happened. Okay, so this is a numeric way for the child to tell us whether things went okay or not. So maybe a return type of 0, a status of 0 says everything's fine, a -1 is something's bad. Maybe you have specific numbers for what kind of bad happened, okay? So, but in any case, to pass it the pointer to an integer, we have to use the address symbol to give it the address of an integer. Okay, so let's start by calling this directly. So I'm gonna steal these two lines here. I think we already have types, but just in case, let's go back here. All right. Shut up. All right. What was I doing? Oh, the wait command. What's this? Context switch. He just starts.
You're gonna see real results lighting up shared memory.
What's going on? Dude's having some sort of fit. No, context switching. It's cool. Just don't even worry about it. All right.
Wait, is that what happens in Tourette's patients?
What?
People with Tourette's syndrome, they just context switch.
All right. So we'll go ahead and do our initial fork. All right. Then we're going to ask the question. We're going to say, if PID is equal to 0, that means I'm the child, right? Else, I am the parent. So if I'm the parent, I might be interested in waiting for the child to finish. Fair enough? All right, so what I'm going to go ahead and do is I'm going to say int status. And then we're going to go ahead and we're going to call the wait command. And we're going to pass in the address of status. All right, let's go back here. All right, so This is a wait when we pass in the address of status, and we are waiting for the only other thread. Now, in this case, we have a specific child ID to wait for, right? That is right here. I want to wait for a specific PID. What PID? The PID of the child that was returned by the fork system call. Then the status, and then a group of options, and somewhere we'll look at where the options are. Are they provided in here somewhere? Yeah, for the wait, no wait. That's weird. We'll look at those here in a second. All right, but we're going to start off with just a wait. All right, since we only have one child, we're going to see how this works. Well, and then we'll go to our Ted. This is a Bolivian Sasquatch.
Those teeth.
He knows how to add fractions.
Does he take a? Does he like eat?
All right, so we're going to go ahead and wait using the default wait system call. And then we're going to have the parent say printf, the child is done, %d, status. So we'll just print out that status. Okay, well, actually, I want to probably leave that in there just as a reminder. Okay, and if we're the child, we're going to go ahead, well, I want to do some counting and stuff, just to, because the child is going to be doing some stuff in our programs, right? So we'll do int I is equal to 0. We can just do that. I is less than 1,000, I plus plus. And we'll do some prints. Child count, %d, I. And then at the end, we can go ahead and have the main return something. So we're going to say return 0 in this case. So if I'm the child, we're going to print out all the numbers between 0 and 999. And then we're going to return a 0. That return is what comes out of the main method for that child. All right, so let's see what these guys should run in the same process space. So this wait should work for this. So let's go down here. We'll exit out of this, and this is fork test, right? Child is done, return 0. Probably should have done some backside. You guys can all read that, right? Especially Pebbles, who's got the 21-inch vision. All right, child is done, 0. Guaranteed the parent waited for this child to finish. Okay, so when this parent forked a child process and we noticed that we were the parent, we can specifically say, I want to go ahead and wait for my child. This wait command automatically assumes it's the most recent child. Make sense? Which means that if I fork a second time, it will look for the most recent child and wait for that one, not necessarily. So you can play a game with the wait command. You know, you have to just like a break breaks out of the most local for loop or most local loop, waits on the most recent child process. But now we want to wait specifically for a certain process ID. So we're going to wait for PID, which is the process ID of our child. If process ID was 0, that means I'm the child. Otherwise, your process ID must be an actual number that is the unique ID of the child process. and we're going to wait for that dude. And I think that options is optional, pun intended. So let's try that.
You have to have
Yeah, it wants
return.
the third one. I think we can actually do that. Oh, doesn't like it. We have to give it options.
Should be 0.
Well, 0 is just it's a static option. Let's make sure we understand what the 0 is for. It's like,
That's what you're
is it-
expecting it for it to return, isn't it?
huh?
That's what you're expecting for it to return.
Well, no. Options is going to be a collection of stuff. I mean, this is the value that gets returned.
Yeah.
This isn't an expectation. This is what thing. It's farther down here. We'll just go look at them. Let's wait. Oh, hold on. I need to call wait PID.
That was supposed to say.
I didn't call the right function yet, because I'm pretty sure this guy is optional. I don't think we have to call that last one. Yeah, that's why I was complaining too many arguments, because wait only has one argument. Yeah, it wants options. Okay, so let's go look at the options. Okay, value of options. Did I bring my phone in here? Did somebody steal it, or did I leave it in my office?
I haven't seen it.
All right.
Your watch pick it up?
Yeah, it did.
Dang it.
Okay,
Is it under the papers?
it is. All right. Hopefully it leaves a message. Okay, so value of options is an OR of 0 or more of the following constants. Return immediately if no child has exited. Also, return if a child has stopped but not traced to ptrace. Status for traced children will have stopped as provided even if the option is not specified. Is that for a process who didn't register with, I don't know when that would get called. It's been resumed by the, maybe this is what you were talking about, Curcio. There's an option that takes in the status where you'll wait until that status is available. So if you want to wait until the child finally gets his act together and finishes what he's supposed to do correctly, the child can keep restarting and you'll wait indefinitely.
That status is for the last child, right? Just the last child?
No, because we're passing in. This is for the wait PID where we specifically give it a process ID we're waiting for.
Does that automatically restart that child if it fails then? Or?
I don't think it's the parent's responsibility. I think it would be the child that would have to spawn a copy of itself to go. So the child, if it failed, it would say, okay, well, I screwed up. So the child then would spawn a copy of itself. If it's the parent, it would return -1. If it was for something went wrong. If it was the child, it would then go and try to do it again. And then it would return, which would then return for the original. And the reason it would return for the original because a memory address was passed in for status. And the wait PID gives you and also wait, almost like punches a hole through memory to give you access to that. So it's an indirect way of accessing inter-process communication. Let's see. I really thought you could avoid giving it anything, which would just be the default behavior. I want to try something here. I think it's null in all caps. Null in all caps worked on yours for weight PID?
Did you save it?
Possibly not.
Didn't work on mine.
And are you using GCC? I don't believe that null in all caps worked on yours.
He didn't, sir.
All right, we're just going to give it a real option. Well, yeah, but here, 0, meaning wait for any child process whose process group ID is equal to that of the calling process.
So, yeah.
Yeah, but that's actually a little dangerous. Wait for.
Doesn't that go until it waits until the child goes, and then if it has children, it keeps waiting until they're all done? But then that's just.
But what if you have multiple children? Yeah, this is anything that's in the group ID. So if this would break. Well, this might give you unintended results if you want to wait only for a very specific child to finish before you did something else.
Wait, so what are you trying to accomplish by trying to pass on the null or whatever? What is the goal?
I just don't want to give it any options, whatever the default is.
So then it waits until what?
Wait for any child process whose process group ID is equal to the absolute value.
That's the child's process. So that just waits.
Meaning
until that
wait
child
for
process is
any
done.
child process. Wait for any child process whose process group. Oh, because this isn't just for.
That's not just for that. I mean,
This is wait as well, not just wait PID. Wait for any, meaning wait for the child whose process ID is equal to. Anything greater than 0. Says wait specifically for that child, and then we can use these specific ones otherwise. So we can just pass it a 1, and that will give us the most control because, well, anything greater than 0 will give us the most control. That says we are waiting specifically for the process ID that we passed in to wait for. If one of the other children from this group finishes, that would be related to another wait, a different wait. So we'll pass it a 1. And then we'll run this. Let me do this for less than 1,000. That doesn't seem like it finished correctly. So I'm thinking that
Isn't it waiting for the child with process ID 1.
No, anything greater than 1 should be, because this is an option. So it says, if this is greater than 0, it's waiting for this exact PID to finish. At least that's how I read the man page. We'll look at it here in a second, but I'm pretty sure that's the case.
Oh.
Yeah, so it said it was done right off the bat. So you think we passed it the PID for option, and that's the specific guy we're waiting for?
Well, you're telling it what you're waiting for, right?
Yeah.
Here's the process ID we're waiting for. Here's the status, and then here's the options. Ay, ay, ay. All right. All right, so they're saying weight PI, the weight system call is equivalent to weight PID -1, passing its status and passing its 0 for option. Option. Oh, this is the value of PID.
Yeah. Options is just below.
So the value of PID can be less than 0, that's any, or less than -1, that's any child process. Greater than 0, which means it'll be an exact processity, which is what we have. So then we want one of these guys then. Or 0 or more of the following constants. WN, W no hang. Phrasing. Also return if a child has stopped. True if the child terminated normally. Status is not null. Okay, yeah, so that's not options. So it looks like it wants us to do, where am I? That's not waiting for that specific PID. No hang says it's an OR of 0 or more of the following constants. So with that in mind, if you put a 0 in there, that would be the result of an OR on nothing. But it seems like they should have a constant that says no option. Like, so. So what, you just put in a 0 unless you have something specific you're waiting for? At the dealio? What is it? This should run like that. Yeah, what's the that? Okay, so this guy should return the shared memory ID. Say this again?
Both names are up top.
Oh, right. I'm looking at this function right here. This function, you would pass in like an array, some memory, and this guy would return this creates the shared memory, this gets the shared memory. Yeah, so this guy is how you get the shared memory ID. Well, this is how you get the actual shared memory between the parent and the child. This guy would give you, allows you to create it. Attaches the shared memory segment located at the address specified. It must be currently attached. Okay, so if we want to create some shared memory, we need this guy, right? And that lives inside of this. So let's go ahead and do that. And we'll make a call to this guy. We want to give it, we can either use malloc to call it, or we can create an array initially and then send it. Actually, it doesn't have to be an array. It can just be an integer if we wanted it to be. Steal that. So we're going to say int mem to share. This guy is going to be equal to 5. And then we're going to say int shared mem ID is equal to that guy. And it wants the pointer, so at mem to share. And then let's prove, well, let's print out the shared mem ID. Print out shared mem ID is %d shared mem ID. And then the other guy here is, steal this whole thing here. I got 1 minute left.
There you go.
I'm not giving you homework anyways. Let me just, we'll finish this next time, but I just want to finish doing what I'm trying to do right now.
So is there like a fork command that does copy this shared, does copy it over? I just feel like
There might be, I don't know if there is.
that would be useful enough that they would do
Int value.
that. You know what? That sounds like really help.
I actually wonder.
I'm surprised they didn't have a price fork themselves.
So wait command has the source code on the manual.
Oh really? Well, I'm sure you can get all this source codes. All of this.
Yeah.
That's all.
I wonder if right in the manual spot.
1 second. That should work. And then this, that should work. Jeff. Jeff.
Where are they?
I got a -1 for the shared memory IDs.